Hey, Benny, welcome to the show.
Good morning, Steve.
I'm looking forward to our conversation, talk about PTFE and emerging lubricious polymer technologies or solutions.
Looking forward to it.
Okay, let's do it. You know, there's been so much talk about this topic over the last couple of years, and it's fairly new, but there's just been a lot of chatter and a lot of good information has come out of it, but there's also been a lot of kind of misleading information. And hopefully you and I can kind of walk through some of those things. There's some real challenges, though, that need to be addressed. And I think this is not a knock against PTFE. It's a wonderful material. There's certainly a place for it. And alternatives can't really fill the gap in some places, but there are some gaps that they can fill. And I want to walk through some of those. But I want to kind of start off, why PTFE has become the gold standard after all these years. And it's still, the right choice for certain applications. But there are some limitations, there's some challenges, and there's some gaps, and there's now better solutions to fill those gaps, and that's what we're going to talk about. Yeah. One of those major constraints is kind of on the supply chain, right? If you look at a major OEM that selects a partner for an extrusion or for a catheter, they always want to mitigate risk, right, by having multiple dual source, triple source, because they can't go down, right? These are life-saving. And that's kind of one of the challenges with the supply chain for PTFE. Over the last couple of years, one of the major suppliers has kind of dropped out, and that's kind of sent some ripples through the industry, right?
Yes.
Do you want to talk a little bit about why PTFE is kind of been traditionally the gold standard, sure, and then we'll talk about some of those. We'll talk about some of those supply chain constraints next.
Sure. So when you look at the chemical structure, PTFE is the most inert and most lubricious polymer in the world, hands down. There's nothing can beat PTFE in terms of its coefficient of friction in natural stage, whether it's dry or wet condition. So it's been used in our industry for over 30 years. Almost every delivery system, catheter that you see out there do use PTFE. And there's the reason behind that. Number one, PTFE, you can achieve a very, very thin wall. I'm talking about under 0.0075 or under half a thousand. It's a paste extrudable or paste extrusion. So there's a lot of times it's much easier to hold thinner wall and tight tolerance. So because of that, in many applications such as microcatheter, using neurovascular, catheter related application, they really require thin wall because every half a thou or every quarter thou really matters a lot. In that cases, PTFE is one of the only polymer that can achieve that thinner. In thermoplastic, which we will go over later on, like the Dynaflex new EverGlide Plus or the SUS new PFX, other extruded product. That if it's a thermal extrusion, there's a limitation how thin it can do, and a lot of the thermoplastic today they cannot be dip coated or film cast. So with PTFE, it's possible that you can film cast it. So that I think that's one of the reasons, and also has a very long biocompatibility history. Everybody know it. FDA knows it. Everybody use PTFE in their application. So I think from a history standpoint, coefficient of friction, also thin wall, that's why PTFE remained the gold standard.
Yeah, as they say in catheter design, profile is king, and if you need a low profile or really thin wall thickness, PTFE has traditionally been the way, especially if we talk about applications and you take one example like aspiration, like clot removal. You need the inner lumen as large as possible to remove a clot, to haul a clot, and your limits are on the OD, the vessel. So what is the factor? What's going to give? It's the wall thickness. There's certainly, as you alluded to, that's where PTFE really shines, whether it's the film cast, which you can get down to half a thou, or the extrusion where you can get, thou, 7.5 tenths, thousandths of an inch. It's kind of hard to beat it in that respect. But not all catheters require that ultra thin wall
Yes.
thickness. So there's certainly a place for these thermoplastic liner technologies. Okay, that's a good overview, and I think people get hung up on coefficient of friction as well. I mean, it's certainly PTFE is the lowest coefficient of friction of all polymers, right? But some of these alternatives also have a very low coefficient of friction, and it's hard to just use that as a guide for material selection. If you think about how they test that, there's some ASTM test, right, where you have this bar and you're rubbing it in a static or dynamic environment. It's more dynamic than that, right?
Correct.
Yeah.
And I think a lot of the material now, it's kind of like engineer been telling me. It's like it's been a long time, since PTFE has existed. So every engineer or a lot of engineers would just take a safer choice, because it's been used before. Let's use it again. But in many applications, we have realized that you don't really need the absolute, thin wall or lubricious property like PTFE. If we talk about neuro, the access to the M1, M2 area, yes, you may need that, because of the tortuous path, the small vessel and all that. But with 90% of the application, let's say under the neck, we have heard from customer that a lot of the thermoplastic alternative like the EverGlide Plus has really served them well. So it wouldn't say that PTFE is an overkill, but it wasn't necessary 100% needed for that specific application. And kind of back to what we talked about, PTFE is a gold standard, but it also have its pain point. We'll talk about all this PFAS, PTO, all this later. But from a design manufacturing perspective, you always have to worry about the etching, because PTFE is the most inert material. So in order to bond it, you have to use a sodium solution to etch out to basically make the surface reactive. So when that happens, if you touch it, if you stretch it, if you do anything to it, it will tend to lose its edge. And when you try to finish a $300, $400 catheter in the final step, and then it gives you delamination, then you have to toss it away. That not only increase the just the material cost, but the overall manufacturing. Because if you have to scrap one catheter, then it's almost enough money to buy half a lot of material, a third of a lot of material. So what we're trying to do, looking in the thermoplastic liner, is really to increase the vulnerability to avoid delamination, because I think this is number one enemy with PTFE from the manufacturing perspective. So if this type of new material is thermoplastic, or ideally even nylon based, it's compatible with the rest of the architecture, then you can eliminate delamination, especially after deflection, after multiple cycling of the catheter. So I don't think PTFE did not become a worse material, but just engineering requirements simply has evolved to a different architecture that we have to look in other option.
Yeah, that's a good point about if you look at just a startup developing a new device, that, because we talked about PTFE is just what people use traditionally. And so that's the predicate, right? But for a device, let's say you're coming up with a new balloon catheter, you're always looking for the predicate because it's already pre-approved and you want to use some material. And so there's payment codes that you can use instead of doing new payment codes. So for a startup and the burn rate, it's always easiest to go with kind of what's been used in the past, because if you have to get it, if it's a totally new device and you have new payment codes, you might be waiting 3 to 5 years and you might not have it. So you try to be as conservative as you can and use what has been used in the past that's biocompatible and FDA approved and things like that. So that's kind of the mindset of why I think people kind of stick with some of these things. And you mentioned delamination. I think I might be wrong, but I think the biggest recalls on catheters are related to delamination. So that's a big issue. The etching is another step, and I think the etching has a shelf life. One of the solutions to that is the tile layer. It kind of locks in the etch, but also gives you some additional bonding, which is really good, cool technology actually, to add such an ultra thin coating over a PTFE, whether it's extruded or film cast, to increase bonding. That's great technology, but if you can avoid a step in the process, you're going to be more efficient, right?
Yeah, yeah.
Yeah.
So I think with the whole architecture we're looking at, it's not along the material itself. We want to look at how the catheter are being constructed. A lot of time the delamination layer is just between the, let's say, PTFE to the jacket or to the braid. So what we have to look at is the interface, between each layer. No
Yeah.
longer look at PTFE fail at this level, or, because of the etching. So I actually have a kind of a little analogy. So Steve, on the kind of the car, a sport car versus a pickup truck, So that kind of illustrated why architecture matter more than the material itself. Because again, we call it like this a pickup truck versus a sport car.
Yeah.
So the traditional PTFE is like sort of like a pickup truck. It's just an analogy. So the PTFE or the braid laser hypotube coil kind of sit on top of the PTFE. So it's kind of like the body on frame design, like a pickup truck. So with the newer technology, like the one that we mentioned with EverGlide Plus, because it's a nylon 12 base liner, so it is actually the same family as the jacket. They're all PA family based. And nylon, PBACs, they both stick pretty well to stainless steel. So it become more like a unibody design, like a car. So the
Yeah.
reason why you can turn a sport car 90 degree a lot easier, a lot sharper than a pickup truck is because it's a unibody design versus it's a body on frame. So that analogy kind of transition to how a physician may want to push or torque a catheter. So physician always would prefer a one-to-one torque.
Yeah.
But if it's like a pickup truck, body on frame, each layer have a micro movement against each other. It's depending on how good the etching, the lamination, and all that is. Then you're not going to be able to turn as well or create a one-to-one torque. So I think that's the illustration kind of show you why architecture itself, or how creating a homogeneous product is more important sometimes than just the material lubricious property, because coefficient of friction is not the only equation
Right.
of making some kind of implant or outer shaft to guide through it with efficiency.
Excellent. That's a great illustration, a great example. Integrated architecture, fewer interfaces, fewer steps, more of a unibody design. That's interesting. Thanks for sharing that. We have another graphic we can go right into if you want to, Benny. I like this
sure.
as well. And everybody knows some of the advantages of, see if I can get that a little bit larger there. PTFE inherently, because of the extrusion process in a linear ram extrusion process and the inherent structure of the material, gives you really good molecular alignment. So it allows you to peel like a sheath, an introducer sheath. And for instance, so there's some really interesting capabilities that come out of that molecular alignment. You can stretch it, elongate, right? And you could reduce the wall thickness further as a secondary process, yes. But that'll also increase your tensile and some of your mechanical properties. But on the other hand, that can work against you in certain applications, right? And I think this visual kind of highlights that. I'll let you talk about that.
So, we started getting a lot of feedback from many different customers and our own study. So one thing that, just like you said, PTFE, have the orientation and the machine direction is great at just peeling it, tearing it, but this sometimes could be a problem. So we did a DOE on a liner using PTFE in the very first stage of the development. So one thing we realized under tighter band, when there's a sharper object, whether it's an implant or another laser hypotube or stainless steel feature, rubbing against that PTFE, it will take a dent. But instead of just taking a dent, it will continue to kind of tear out the material. And sometimes some of the fibers will come out because the PTFE strength being stripped out. So that could be a problem. So then we went in and tried a couple other, approaches, standard P bags, but it was too tacky. We do Vestamet ML21. It was too hard, but still not lubricious enough. So we ended up, integrating the EverGlide Plus 60 durometer, the high durometer version of the EverGlide Plus into the structure. And yes, we do have damage when the implant is a sharp object that going through the ID when we use the EverGlide Plus, but the failure mode is slightly different. It's more like a cutting board creating a dent versus like like a banana, like a PTA, it would just
Yeah.
peel. So we have see a little bit different failure mode. So in that application, that fuel application, that has proven to be a better choice to use this because of the failure mode of the material.
Okay. That's a great illustration. And one example of that, perhaps, is if you think about a stent that's crimped, right?
Yeah.
To be loaded into a sheath, let's say a nitinol stent. And depending on the radial force of that stent that's loaded into that sheath, if you have, let's say, a weaker film cast PTFE liner, that's going to dig right into it, right? And it's going to not deploy as easy. It could also dig into an extruded PTFE liner, depending if it's oriented or whatever. But that's a good example, I think, is a stent loaded into a sheath that has tremendous amount of radial force to be released that could potentially cause some kind of like little skiving, and it'll just rip through, like you mentioned. Is that kind of an example of maybe an application?
Yes. And then this also kind of lead to the extension of what we just discussed. Sometimes you want a more rigid material that more abrasion resistant for avoid digging or to be as close to the brush's property compared to PTFE. But in some application, you want it to be as soft or as elastic as possible. The case we talked about earlier, maybe for some kind of stent delivery system, but
Yeah.
now you have some other, let's say neuro product that you want to have a very soft distal end, but you still want to maintain some kind of rigidity in the proximal. So in this case, I think this is where thermoplastic liner, shine, because you can weld them together. You can connect different section. So now not only the PVAX jacket have the ability to wear a durometer. Now, if your liner can also wear a durometer, then I can have a standard catheter all the way to the last, let's say, 10 centimeter, and I can transition to a softer line. Because like material like EverGlide Plus we discussed, the early example was a 60D version. So now I can actually do a 20D version of that liner for that specific type of application. And the flex modulus is only like 5 times, or less than 10 times of PTFE. So now you have a choice to get your distal end of your catheter more flexible than your competitor. So I think this is really where the lower durometer or different durometer choices of liner give R&D engineer more flexibility, but not just focusing on the jacket or the braid or the laser cut hypotube structure. There's another benefit.
That's a really excellent point. We're all familiar with varying the durometer along the outer jacket, maybe from 72D down to 25 on the tip or 35. And then your liner's fixed, right? It's 53D for PTFE roughly, but the ability to also vary the inner liner durometer is another key advantage, especially for some of these applications where you need extreme flexibility on the distal and neurovascular, for instance, where you can maybe do a 25D on the liner. And traditionally, that 25D of PBAX is really tacky, but with EverGlide, you're avoiding that tackiness as well. So you hit it on both sides.
Yeah. And then also we find a really interesting application, or a lot of interesting application, but it's led by something like laser hypotube, which is now a lot of architecture going to that direction. So for the longest time, the biggest challenge for people using laser hypotube is how do you have a liner that's securely bound in the ID of the laser hypotube. But because, it is a PTFE, even if you edge it, it doesn't really bond to a stainless steel. You have to count on the reflow window, the curve, or the jacket to sink in to bond to it, or you can add a tie layer, but those are not ideal choices because it will still tend to delaminate over time when you flex it. And also, imagine back to our conversation earlier, in the very distal tip, how do I get it more flexible? If I'm still restricted by a high stiffness polymer like PTFE, then doesn't matter how good of a laser cut pattern I get at the distal, it's still going to be somewhat rigid. or you can force it, but you may brittle fracture that liner material. So now in that kind of application, the lower durometer thermoplastic will come into handy. Number one, it will naturally bond to the stainless steel because it's nylon based. So you solve that reflow window curve wave problem. And then not only that, because it's a lower durometer material, so it will allow that distal section to flex better because it's more elastomeric, lower yield
Yeah.
point, flexible. So that is kind of a big discovery we have found that a lot of people are wanting to utilize this material in a challenging design using laser cut.
Very interesting, because we've seen the massive growth of a laser cut hypotube for reinforcement in some of these modern catheters, especially steerable catheters, transeptal, electrophysiology, structural heart type applications, where there's higher, and like in a structural heart, higher deployment forces. But there is one of those challenges where you're reflowing the material within the curves of the laser cut patterns, which affects flexibility. So you're talking about, this is kind of where you're headed with that, right? You're not necessarily loading those kerfs with a material to kind of bind it up. And if you do, it's with a super low durometer material.
Correct. Correct. So the material actually feel like a rubber band.
Yeah.
Feel like a I don't have a sample with me to show you, but it feels like a rubber band that's still lubricious. So meaning
Yeah.
that you can still flex it, like a PBAX 25D, but now you have a much lower coefficient of friction, so that whatever inside can glide through that tighten.
Yeah.
Yeah.
I'm going to throw you off a little bit on this one. We were talking a little bit about film cast, right? And for ultra low wall thicknesses, and in some cases there's a tile layer added to that of a PBAX or a TPU or a nylon. Have these compounds, EverGlide compounds, ever been solutionized such that they could also be used as a potentially as a film cast component?
Yes, that's definitely something that we're looking into. We're working on. No, definite answer at this point. How we
Yeah.
can approach it, but another thing that we realize with this material, you don't. There's a two reason why I mentioned you don't necessarily. Number one, you don't necessarily want a really thin wall to start with because it's a thermoplastic. So
Yeah.
meaning that you have a metal structure, let's say a coil, that you have to coil it with high tension. Otherwise, the pitch will get kind of, become inconsistent.
Yeah.
So with such a thin wall, then you may have a more problem with break exposed or coil metal exposed in the IV of the material. So in that case, you don't necessarily, it's not the best advantage to get a really thin wall. And the second approach, or the second answer to that, because this is thermoplastic, it's a nylon base. So meaning there's no etching on the surface, right? So meaning that you can stretch the material kind of as much as you want. Unlike something like PTFE, if you stretch it a little too much, it may start losing the edge. But this is a nylon material. So we actually have ourselves stretching material from 1.5 dowel wall on the proximal end and thin it out to about like under half a dowel wall at the distal. So we can have a machine to do it, to stretch it with consistent force. And again, because it's a thermoplastic, so the advantage of it is it doesn't get etched. So, it doesn't matter how you mesh the surface. The other PBAX material, jacket and all that is still going to bond to that. So that's kind of answer to your question.
Yeah. Okay. Thank you. This is great. Let's move on to a couple things to wrap it up. Sterilization, and then kind of some of the FDA guidance that we can kind of talk about the sterilization aspect, which is a big one as well.
Yeah. So, I mean, as you're aware of, there's some, big lawsuit went on a couple of years ago with ETO, so the EPA really tightened down on the emission regulation on ETO. So sometimes it costs longer lead time, higher price, and, more like a future regulatory or environmental concern to the industry. So a lot of people are looking for alternative, like hydrogen peroxide, autoclave, E-beam gamma. So E-beam and gamma is the probably cheapest, fastest way, to do sterilization. But the only reason why it cannot be used in many devices is because PTFE. If you do an E-beam, it will gamma, it will damage the PTFE. So there's a lot of change or a lot of talk about now what is the best alternative to ETO. And a lot of thermoplastic liner, like the EverGlide we talked about today, has proven to be E-beam stable. So meaning now you have one less regulatory concern in the future. And it's cheap.
Excellent point. Okay, excellent. Benny, this has been a great conversation. Is there anything else we should cover?
Yeah, I mean, in the end, I just want to summarize it. So PTFE really earned its place as a gold standard, and it will remain the right solution for many, torturous paths, demanding catheter application. But what's exciting today is that engineers have more tools than ever before. You're not stuck with one single material. So the question is no longer, which material has the lowest coefficient of friction. So the better question is which material enables the best catheter architecture, for this specific application. I mean, if the engineers start asking, or if we start asking the question at the beginning of every program, I think we'll continue to build better devices and, for physician and to benefit ultimately the patient.
That's a great way to close. It's all about the patient.
Yes.
Yeah. Benny, it's been great having you. This has been a great conversation. And I forgot to mention, but this podcast is kind of a continuation of the white paper series, right? You did a great white paper that's on Chamfer, and we'll put a link on there to talk about some of these things. And there's another version coming out, which will also have you on the podcast to kind of go through that as well. So
that will be more exciting, I think.
Yeah. So we'll make sure to put a link. That's a really good resource that you wrote. And I know we're working on another one, right? The kind of second chapter, so to speak, and we'll be able to talk about that. So we'll make sure everybody has a link to that and so they could read up on it and be prepared for the next one, Benny.
Yeah. Thank you, Steve.
All right. You're welcome.